Hello, my name is Alyssa Carell, and in this video I'm going to be explaining to you my knowledge on van der Waals equation of state. So let's get started. First of all, here we have van der Waals equation of state, and it looks kind of similar to the ideal gas law. But the only difference here is this applies to non-ideal gases. So this first section here looks very similar to our ideal gas law, the only exceptions being this bottom term here, and we're missing our n factor. So the reason why is this V right here stands for our molecular volume of our compound that we're using. So this would be however much volume 1 mole of our compound takes, which is why we don't need that n mole factor. And then this B value here is our actual volume of our compound, of how the volume that all the molecules in our compound take up. So this next section here, however, this is our attraction component of our equation. So A right here is our attraction constant. So now let's get started. So in order to graph this out, let's take a pressure versus volume graph. So if we were an ideal gas, our graph would look something similar to this. Now, at this certain temperature value, it would look something like this. Now, at other temperature values, as we start getting lower and lower, they start to hit this point of inflection. And at this point of inflection, we have our critical point. Now, because this critical point is located at a point of inflection, we can write our first derivative as equal to 0, and our second derivative of the critical pressure is equal to 0. So now let's go ahead and write those out. So our first derivative is going to be equal to negative R times our critical temperature over our critical volume minus B squared plus 2A over critical volume cubed, and that is equal to 0. And now our second derivative is going to be equal to 2 times R times our critical temperature over our critical volume minus B cubed. That's going to be minus 6A over our critical volume to the fourth, and that is equal to 0. Now, because this 2 and this 6 both have factors of 2, we can get rid of that and turn this to a 3. Okay, so now let's rearrange these equations a little bit. So this first one, we can rewrite it as 2A over our critical volume to the third is equal to RTC over our critical volume minus B squared. And we can also rewrite our second one as 3A over our critical volume to the fourth is equal to RTC over VC minus B cubed. So now what we want to do is we want to solve for B. So let's go ahead and write that down here. Solve for B. Now in order to solve for B, we're going to take this first derivative here and we're going to multiply it by the reciprocal of our second derivative. So that's going to give us 2A times VC to the fourth over VC to the third times 3A. And that's going to be equal to RTC times VC minus B to the third over VC minus B squared times RTC. Now we can do a lot of canceling here. So first thing we're going to cancel out is these A's. And then we can also cancel out this VC and the exponent. Now we can, over here, we can cancel out our RTC, we can also cancel out this whole term right here and the exponent here. So what that's going to leave us with is 2/3 BC is going to be equal to BC minus B. Now rearrange that a little bit, and we have B is equal to 1/3 BC. So now we're going to do this same thing, except where we're going to solve for A. In this, though, for solving for A, we're going to take our B factor here and we're going to plug it back in to our first derivative. So we're going to say 2A over BC cubed is equal to RTC over BC minus B, which is our 1/3 BC. That whole thing is squared. So this right here can be rewritten as 2/3 BC. So now let's simplify a little bit, and we're going to say 2A over BC cubed is equal to RTC over 2/3 BC squared. So that's going to be 4/9 BC squared. So now what we're going to do is we're going to take this BC and we're going to multiply it to the other side. So get rid of that. We add it here. You can see that this cancels out and that cancels out. And then now we're going to divide this whole thing by 2. So what that's going to leave us with is A is going to be equal to 9/8 times RTC BC. And that's our A right here. So now we're going to take our B and our A and we're going to plug them back in to our original equation. So that's going to leave us with our critical pressure is equal to R times our critical temperature over B minus 1/3, or BC minus 1/3 BC. It's going to be minus 9/8 times R TC VC all over BC squared. So now let's do a little bit of canceling here. And so this is going to cancel out and that's going to cancel out. And so we can also see that with this simplified to 2/3 BC, that each of our terms in the equation here has an RTC over VC value. So we can factor that out and say our critical pressure is equal to R times our critical temperature over our critical volume times 2/3 minus 9/8. So as we can see here, this will end up equaling 3/8. And we want to go ahead and rearrange this equation to where all of our variables are on one side. So that's going to leave us with 3/8 is equal to our critical pressure times our critical volume over our R times our critical temperature. And this thing here is going to be equal to Z, which is our compressibility factor. So it's compressibility factor. And this is the compressibility factor for any non-ideal gas in critical conditions. So the relevance of this is that it can be used to plug back in to our original equation and find the actual values of A and B. And those can be used to find the critical pressure, critical volume, anything you could use in this equation for any non-ideal gas under critical conditions. Because as you've seen before, we have had no data when it comes to like what compound we're using or anything like that before starting this calculation. So this is a general solution for all non-ideal gases in critical conditions. So let's go ahead and do that. So what I'm going to do is I'm going to erase here a little bit. I'm going to rewrite A and B. So A is 9/8 RTC BC. B is 1/3 BC. And our C is equal to PC times BC of RTC, and that is equal to 3/8. So now let's erase all of this here. And what we're going to do is I'm going to plug this back into our original equation, or plug this Z value into our A and B parameters in order to find their actual numerical value. So first thing, let's go ahead and solve this for VC. So if we rearrange this equation a little bit, we're going to get VC is equal to 3/8 times RTC over PC. So now let's plug this back into these equations for VC. So for our A, or let's start out with our B actually. Our B is equal to 1/3 times 3/8 times R times our critical temperature over our critical pressure. Now these 3's here will cancel out, and that leaves us with B is equal to R times our critical temperature over 8 times our critical pressure. And that is our actual value of B for any non-ideal gas in critical conditions. So now let's do the same thing with A. So for A, we're gonna have that A is equal to 9/8 times R times TC times 3/8 times RTC over PC. So we're going to go ahead and multiply these fractions together, and that's going to give us 27/64, and that's going to be times RTC times RCC. That gives us R squared times TC squared, and that's going to be over PC. And like I said before with the B, this is our A value for any non-ideal gas in critical conditions. So that's all I have for you today. Thanks for watching, and I hope you learned something.